All right, today we're diving into a really cool puzzle in organic chemistry, nucleophilic aromatic substitution. Basically, we're going to look at how chemists figured out how to hack one of the most stable and kind of stubborn structures in all of nature, the benzene mix. So here's the fundamental problem, right? A benzene ring is just this big, happy cloud of electrons. And a nucleophile, well, it's also packed with electrons, and it's looking for something positive to react with. Trying to get these two to react should be like pushing the negative ends of two magnets together. They just want to repel each other. So how in the world does this reaction even happen? Well, you're right. Under normal circumstances, it's not going to happen. But chemists are clever. They figured out that if you set the stage just right, you can actually overcome the ring's natural defenses. And it turns out there are two main playbooks for pulling this off. And these two approaches couldn't be more different. First, you've got the strategic attack. This is where we cleverly weaken the ring from the inside, making it vulnerable. The other approach, pure brute force. This is the kick the door down method, where we use extreme conditions to just force a reaction to happen. Let's start with the more elegant, strategic method first. This first path is called the addition-elimination mechanism, or just SNR for short. Think of this as the surgical strike. It doesn't work on just any old benzene ring, oh no. It requires a very specific setup for it to even have a chance. So what's on the checklist? First, you need a leading group already on the ring, something like a halogen that can get kicked off. Second, and this is absolutely critical, you need a powerful electron withdrawing group. And its location is everything. It has to be in the ortho or para position relative to that leaving group. That's non-negotiable. And finally, of course, you need a strong nucleophile ready to make its move. The mechanism itself is a pretty logical two-step dance. First, you have addition. The nucleophile swoops in, attacks, and forms a new bond. But in doing so, it breaks the ring's most prized possession, its aromatic stability. Then comes the second step, elimination. The leaving group says, see ya, takes its electrons, and leaves. This allows the ring to breathe a sigh of relief and snap right back into its super stable aromatic state. Addition, then elimination. Simple as that. Now, that thing you form in the first step, that temporary non-aromatic intermediate, has a special name, a Meisenheimer complex. Now, normally, this thing would be screaming with instability. It's got a negative charge, and it's not aromatic. But this is where that electron withdrawing group becomes the hero of the story. It reaches in, pulls that negative charge out of the ring, and spreads it out over itself through resonance. It stabilizes the whole structure just long enough for the reaction to proceed. Without that EWG in exactly the right spot, this whole thing falls apart. Okay, pop quiz time. In most other substitution reactions you've probably learned about, like SN1 and SN2, iodide is the best leaving group because it's big and stable. So, looking at this list, which halogen do you think makes the SNAR reaction go the fastest? Go on, take a guess. And the answer, which might seem totally backwards, is fluorine. Yeah, this completely flips the script on what we normally expect from leaving groups. And if that feels weird and counterintuitive to you, good. It means you're paying attention, because it points to something really unique about this mechanism. So what's going on? Here's the key. The speed of this reaction isn't about how easily the leaving group leaves. The rate-determining step is that first step, the attack. And the speed of that attack depends entirely on the stability of that Meisenheimer complex. Fluorine is the most electronegative element there is. Its power to cull electrons towards itself through induction is just off the charts. It does the absolute best job of stabilizing that negative charge in the intermediate, which makes that first step easier and faster. It's all about stabilizing the intermediate, not about being a good leaving group. But what if you don't have that handy electron withdrawing group? What if you just have a plain old chlorobenzene and you still want to do the reaction? Well, you can't be strategic anymore. You gotta bring out the big guns. This brings us to pathway number 2, the brute force elimination addition or benzene mechanism. The shopping list for this reaction looks totally different. No electron withdrawing groups needed. Forget about them. Instead, you need an unbelievably strong base. We're talking things like sodium amide. And on top of that, you usually have to crank up the heat and pressure. These are not gentle, subtle conditions. This is chemical heavy metal. And look at this. The order of operations is completely flipped from what we saw before. Here, it's elimination first. That super strong base comes in and rips a proton right off the carbon next to the leaving group. This triggers a cascade, and the leaving group gets kicked out. Then comes addition, where the nucleophile attacks the crazy intermediate that's left behind. And what is that crazy intermediate? It's a thing called benzene. And it's one of the weirdest molecules in organic chemistry. It's a benzene ring that has what looks like a triple bond in it. Now, this is not a normal, stable triple bond. It is highly strained, incredibly reactive, and it exists for only a fraction of a second before it reacts with whatever it can find. You could think of it as pure chemical dynamite. So, we've got two completely different ways to get to a similar result. We have the strategic SNR pathway and the brute force benzene pathway. Let's put them head to head to really nail down the differences. This table really lays it all out, doesn't it? Let's just walk through it. For the substrate, SNR absolutely requires that electron withdrawing group. Benzene doesn't need it. For the base, SNR is fine without one, but benzene demands a really strong one. The intermediates couldn't be more different, the relatively stable Meisenheimer complex versus the wildly unstable benzene. And check out the leaving group trends. They are the exact opposite of each other. That's a huge tell. And finally, the products. SNR is clean. It gives you one predictable product. Benzene? Well, it's messy. It often gives you a mixture of products, which is a big deal if you're a chemist trying to make just one specific thing. Okay, so that's the theory. But theory is only useful if we can apply it. So let's try to solve a problem just like you would in the lab or on an exam. All right, here's the setup. You've got plain old chlorobenzene. Notice, no activating groups on there. But you're hitting it with sodium amide in liquid ammonia. That's a really, really strong base. So what do you think? Is this a job for the strategic attack or the brute force method? Yep, you got it. That is a textbook classic case for the brute force benzyne pathway. The lack of an electron withdrawing group immediately rules out SNA, and the presence of that monster base, sodium amide, that's the giant flashing neon sign telling you we're going through benzyne. The conditions always tell the story. But wait a second. This benzene intermediate, it's super high energy, it's gone in the blink of an eye. You can't just put it in a bottle and look at it. So how do we actually know it's real? How do you prove something exists when it disappears almost instantly? The answer is just brilliantly elegant. We set a trap. You run the reaction, but you throw in another molecule whose only job is to catch the benzene if it ever forms. Here's how it works. You do your benzene reaction under the usual harsh conditions, but you toss in a molecule called furan at the same time. Now, it just so happens that benzene is a fantastic partner for a reaction called a Diels-Alder reaction, and furan is the other perfect piece of the puzzle. The moment any benzene is formed, it gets instantly snatched up by a furan molecule, and they snap together to form a very specific, very stable product. When you find that final product at the end of your experiment, it's like finding a footprint at a crime scene. It is undeniable proof that benzene had to have been there to create it. Pretty cool, right? Okay, so let's boil this all down. What do you really need to remember? 1. SNR is the strategic addition then elimination path. It needs an electron withdrawing group to stabilize that Meisenheimer complex. 2. Benzene is the brute force elimination then addition path. It needs a super strong base to make that crazy benzene intermediate. 3. The reaction conditions tell you everything. Look for an EWG or a strong base to know which path you're on. And finally, don't ever forget that those leaving group trends are completely opposite for the two mechanisms. And that leaves us with a final thought. We started with a molecule that seems, for all intents and purposes, unbreakable. But we found two totally different ways to get in, one with strategy, one with force. It really makes you wonder, what other chemical fortresses are out there just waiting for chemists to find the right key, or maybe just a bigger hammer, to crack them open?